Hello everyone, it's March 18th. Alright, let's do this. Minimum operations to make binary array elements equal to 1. You're given a binary array. Is there a Wikipedia page for this? Nope. It's just hover. New feature. You can do the following operation on the array any number of times. Choose any 3 consecutive elements from the array and flip all of them. Flipping is just turn 0 to 1, 1 to 0. Turn the minimum number of operations required to make all elements equal to 1. If it's not possible, return -1. Huh. Any 3 consecutive can be flipped, which means any 3 we can flip, any 3 we can flip, and then we want to know if it's possible to flip everybody to 1. I try to find a minimum, right? The minimal number. Have no idea just by looking at this. All right, so if we want to find something that is going to be flipped to, so if it's already a 1, right? Yeah, if it's a 1, we might flip it to 0 and then flip it back. That is fine. I think the question is if you have a 0, right? If you have a 0, you definitely want to flip it. So if we go left to right, okay, and if we already have 1 and a 1, how to say? I think if from left to right, if you already have some 1s, you probably want to keep them. You don't want to flip them. But the first 0 you see, yeah, that need to be flipped, right? That need to be. You might want to flip the first 0, okay? And the only way to flip is just starting from there and then flip, right? Imagine we have a bunch of 1 and now we have some 0, right? Or have some, that doesn't matter, whatever it is. So these you don't want to flip because there's already 1s. If you flip it, it doesn't give you any good. Now you find the first 0, and of course you can flip using these 3, but then you actually propagate 0 to the left, so you don't want to do that. You want to propagate 1. So you flip these, that become 1 0 0, right? And then move on. Or you'll flip these, then they become 1 1 1, and then move on. You'll flip this become 1 0 1, and you cannot flip anymore. I wonder if that is the answer. We can give some Alright, just take a look and then we'll practice and see how it goes. So the answer is -1, right? The answer is -1. So I wonder if we can just go this way. It's almost like greedy. We just need to prove it. So basically what we want to prove is whenever we see a 0, right, with everything to the left is 1, or 0 is the first one, then we'll always flip it with 0 at the beginning. I think that is correct, because you either do it that way or you have to sacrifice. You have to get more zeros on this side. And you, like, if this, so our hypothesis is the greedy, right? The hypothesis is whenever we see a 0, with everybody in the left is 1 or nothing in the left, then we should always flip it starting from the 0, and this will produce the minimum number of steps. So the counter argument is, if this doesn't work, so we we'll say, okay, in order to do this, we'll do like a, like this, right? We will flip it with the first 0 not being the first element in the flip. So if we do that, we'll definitely get it to 1, but then we produce new zeros, right? We'll produce new zeros. Oh, you might be able to save steps down, but these new zeros need to be dealt with. And since they're all 1s, it's actually getting harder to deal with. So therefore, I think greedy will work. Well, it's not a very foolproof or very good proof, but conceptually, I think it makes sense. And I am just going to do it that way. Hopefully, we hit on the right spot. Ugh. So what we need now is to go. Right? We go find the first 0, and now we'll flip. Right? We'll flip. For this, flip, and then move on to the next. If it's 1, move on to the next. If it's 0, we're basically okay. So I smaller than, actually it can be nums dot length dot size minus 2. All right. I would say if nums I is equal to 0, then I say nums I equal to 1, nums I plus 1. I believe if it's a 1 becomes 0, so it's gonna be exclusive or 1, right? So if it's a 1 becomes 0, if it's a 0 become 1, and nums I plus 2 exclusive or 1. Alright, so we do that, they'll guarantee that everybody will be 1. So once this one's done, when we get out, we also need to say rest equal to 0, because I need to count. So every time we do this, we'll plus equal to plus, right? And then at the end, we say if nums dot size minus 1 is equal to 1, and nums dot size minus 2 is equal to 1, right? If these both are equal to 1, then I'll return rest. Otherwise, I'll return negative 1. All right. We are going to try. I'll call this greedy. Greedy solution, right? Where we always start the operation starting from the first 0 bit in vector. Ooh. Alright, let's check if it's right. Oh, it looks solid. I'm going to submit it. Yep. And it works. If we think about it, yesterday is also bit manipulation. Maybe that was the theme. Maybe bit manipulation is the theme. We start by flipping 3 consecutive elements to try to transform all zeros into 1. First, flip the subarray 0, 0, 1, changing the array into this, then flipping 0, 0, 1. And finally, if a 0 appears near the end of the array, especially within the last 2, we cannot flip it using a full triplet. This means that if any 0 is left in the last 2 after processing, it is impossible to make. Since a single flip affects 3 elements, each flip we apply has a lasting effect on the next 2 indices. Instead of modifying the entire array and recomputing values every time, we need a way to keep track of the flips already applied. This is where we introduce a deck to store the indices of past flips. The deck allows us to efficiently determine how many times each index has been flipped by keeping only the flips that are still affecting the current index. We iterate through the array. Okay, I don't quite understand what it's trying to say, but dude, this one looks very simple. I have a flip queue. Okay, if it's not empty and I is larger than flip q dot front plus 2. So basically, flip, I have a front and I have a back, right? So I've said if the front, if current I is larger than front plus 2, so the outside nums plus nums I plus flip q dot size is equal to 0. Nums is either 1 or 0, right? So flip q is getting flipped. I don't quite understand. Check if nums I needs flipping. What do you mean? Check whether it needs to be flipped. At each index, I will first remove an outdated flip from the deck, and those that were applied more than 2 pointers earlier, as they no longer affect I. Next, we determine whether we need to flip at index. The second key observation is that the effect of a flip is cumulative. If an index has been flipped on odd number of times it has effectively changed its value, whereas if it has been flipped even number, it remains the same. Using this property, the value plus number of active flips affecting I. If it's divisible, which means number of active flips. Number of active flips. I don't quite understand. So within, I add them, right? Then we say flip q. I don't understand. Flip q dot size. Let's say flip q was only 1. If it's a 1, then we need even number. Odd number. No, an even number. If it's 0, then we need to see if the previous has size is 2 and 0, then we're saying we're flipping 0 and what was the observation again? Keep track of the flip already applied. Yeah, you put index in it, and if it's too much, you will. So basically, every time when we add a new one, then we have the previous one, right? Then we decide. Yeah, I don't understand. I don't understand. The effect of flip is cumulative. If an index has been flipped on an odd number of times, it has essentially changed its value. Original value. Let's say original value is 0. Number of active flips. Oh, it's number of active flips. Active flips, like how many has been flipping? So it's either flip 0 times or 1 time or 2 times. So after that, it will no longer be flipped. Ah, that makes sense now. So that's why we use this plus this mod 2. So if I'm 0, then I want even number of flips, because that will turn me into 0 still. Now you want, don't you want odd? Right, the current is 0. If the result is 0, that means nums I currently is 0. So we must flip it. Because if it's 1, if it's 1, I still don't quite understand. I think flip Q is just a call who has been flipped. So if you only have 1 that getting flipped, so you gotta influence 1. So if you have 2, then you gotta influence twice. Right? You're gonna influence twice. And now we are deciding whether we need to flip this. Right? So if it's a 0, then we need the flip Q size also to be even. Right, which makes sense. So if nums I is odd, then we need the other one to also be odd. Because if the other one is even, then still be no change for the current. Alright, I guess it's my work. I think sliding window is much easier. Yeah, I think sliding window is much easier. Ooh, accumulate. I didn't know that. C++ has accumulate. So what does this sum do, actually? I think it's just a sum, everything. So then you can compare sum is equal to. Well, makes sense. Makes sense, we're doing the same way. Bit manipulation and greedy. If it's 0, we'll turn it into 1. Oh, this is exactly the same as my solution. And it's actually the same as the greedy as well. Okay, I think that will be it. Oh, I'm fighting the sleepiness. I'll see you guys tomorrow. Adios. Boy, do I want to sleep now.